Hello friends, we have studied normal groups, subgroups in group theory. We have defined normal subgroup and we have studied some properties of normal subgroups in terms of lemma. Now we shall consider problems on normal subgroups. I have written here some problems and we shall solve them one by one. Now see what is the first problem. If G is a group and H is a subgroup of index 2 in G, prove that H is normal subgroup of G. Now we consider the solution of this. First problem. G is group and H is subgroup of index 2 in G. So what is meaning of index of a group in G? Number of right or left cosets. Distinct number of right or left cosets is known as index. So that means H has two right or left cosets in G. So this is given. Since H is of index 2 in G, so the first solution I shall write here. Since H is of index 2, the number of distinct right or left cosets of H in G is 2. That is the meaning of index. Number of distinct cosets, either right cosets or left cosets of H in G is 2. Now let A belongs to H. Then consider an element in H. Then what we have? We consider the left coset AH, and that is equal to the right coset, and this is equal to H. So this is the result when A is in H. Now this follows by closure property. A is in H, an element in H. So product of two elements in H is again H, and therefore AH is equal to HA is equal to H if A is in H. Now further, if A is not in H, then AH will not be equal to H. This left coset is not equal to H, and the right coset is also different because A does not belong to H, and therefore this will not be in. If A is in H, then it is equal, and HA is not equal to H. But the number of distinct cosets of H in G is 2. That is given. Since total number of distinct right or left coset of H in G is 2, G is decomposed as, or G is written as, or G is, we can simply say, expressed as G is equal to H union AH, or G is equal to H union H. So we consider two cosets, left coset. H can be considered as left and right as well, because we have H is equal to EH, or identity element, and therefore G can be written as union of these two cosets, left cosets, or G can be written as union of these two right cosets. And since the A is not in H, so we have AH and HA here. G is expressed in terms of these two. And further, if but H has no element common with AH. No element in common. Why? Because these are distinct right cosets. These are H and AH are distinct right cosets. We have seen here AH, if A is in H, then AH is equal to H. So this H and AH are different, and therefore H and AH have no element in common, and therefore we must have this AH is equal to HA. Then only G can be decomposed as a union of these two cosets. Therefore we have we must have this AH is equal to HA. That is, left coset is equal to right cosets. And this proves that H is normal. H is normal subgroup of G. So this is A belongs to, A does not belong to H, but A belongs to G here. And thus this proves that H is normal subgroup of G. This is a lemma we have proved. Every left coset is equal to right coset, and or left coset is equal to right coset, then H is normal subgroup of G. So this completes the solution of first example. If G is a group and H is subgroup of index 2 only, then G can be written as H union AH or H union HA. And these two have no element common, and therefore this AH must be equal to HA, and A belongs to G. So therefore this proves H is normal subgroup of G. Now we shall consider the second problem. See, what is the second one? If N is normal subgroup of G and H is any subgroup of G, prove that NH is subgroup of G. So it is given N is normal subgroup of G. We consider that first. N is a normal subgroup. Normal subgroup of G. And let A belongs to G, an element in G. Then we have AN is equal to NA. This is by condition of normal subgroup. A subgroup is normal if and only if we have left coset is equal to right coset. We have used this property in first solution also. Now H is a subgroup of G. Let A belongs to H. If A belongs to H, then what we will have is AH. Then this element AN is equal to NA for all A belongs to H, and that means for all A belongs to G, because H is subgroup of G. For all A belongs to G, since H subset of G. H is subgroup of G means H is subset of G. If an element is in H, then the element A is in G. So therefore we have if A belongs to H, then AN is equal to NA. Now you see what if for every A belongs to H, this is AN, and which is equal to NA. So this implies the set Hn is equal to NH. because here A belongs to H. So therefore this A into any element in N will be in Hn, and this belongs to any element in N and A is in H. So therefore this will be NH. So this equality AN equal to NA implies HN is equal to NH because this A is in H. And thus if we have two subgroups H and N such that Hn is equal to NH, then this implies or this proves Hn is a subgroup of G. So this in the further, therefore Hn is a subgroup of G, or this further implies Hn is subgroup of G. See, we have proved this as a lemma. You refer that lemma, let maybe lemma number 8. We have H and K are two subgroups of G such that Hk is equal to Kh. Then Hk is subgroup of G. So here we have Hn is equal to Nh, therefore Hn is subgroup of G. And this completes the solution for Hn or Nh, it is the same, and subgroup of G that we have proved. Now we shall consider the third example, third problem, and solution for the third problem. Now see, the third problem is show that the intersection of two normal subgroups of G is a normal subgroup of G. We shall consider the two normal subgroups as N1 and N2. Let N1 and N2 be two normal subgroups of G. And what we have to prove? We have to prove their intersection. Their intersection is also normal in G. To prove N1 intersection N2 is normal subgroup of G, we have to prove that, or we shall prove that, consider A belongs to or G belongs to G. Definition of normal subgroup. We shall prove that for all G belongs to G and N belongs to N1 intersection N2, G N G inverse belongs to N1 intersection N2. So this is what is a requirement for the normal subgroup. G belongs to G and an element in the group, in the set, then that or in the subgroup, then that must imply G and G inverse is also again in the same subgroup. Then that subgroup becomes normal subgroups. Now let G belongs to G, that is considered, and N belongs to N1 intersection N2. Now N belongs to N1 intersection N2. So this implies N belongs to N1 and N belongs to N2. It is in intersection means it is in both sets. And we now consider the given condition that N1 and N2 are normal subgroups of G. Since N1 and N2 are normal subgroups, of G, we have G belongs to G. For all G belongs to G, N belongs to N1. See, N is in N1. We assume N is in the intersection of N1 and N2. Implies G n G inverse belongs to n1 because n1 is normal, and for all G belongs to G, n belongs to n2. And this will imply, because n2 is normal, G n G inverse belongs to n2, and thus G n G inverse is in the intersection. It is in n1, it is also in n2, and thus we have G n G inverse belongs to n1 intersection n2 for all G belongs to G, n belongs to n1 intersection n2. We have considered n belongs to n1 intersection n2. That means it is in both. And then we have considered G belongs to G. Definition of normal subgroup is applied for both n1 and n2. And further, this implies the element is in common for both n1 and n2. It is in the intersection. And this proves that n1 intersection n2 is a normal subgroup of G by definition. So hence n1 intersection n2 is normal, or that is intersection of two normal subgroups is, or we may consider the words the same, hence the intersection of two normal subgroups. Here it is n1 intersection n2 is a normal subgroup of G, and this completes the solution for the third problem. Now we shall consider the fourth one. Solution of 4. See, the fourth problem is, if H is a subgroup of G and n is normal subgroup of G. H is only subgroup but n is normal subgroup. Show that H intersection n is a normal subgroup of H. See, the relative considered here is of H, not in G. We have to prove H intersection n is normal subgroup of H. So first n is given as normal subgroup of G, that we shall consider. That is solution for the fourth problem. And here what we have to prove is, by definition of normal subgroup, consider an element of H and show that, and consider an element A in H intersection n. Then we have to show H inverse is again in H intersection n. Then that will be normal subgroup of H. So we shall start like this. Let, given that n is normal subgroup of G, n is a normal subgroup of G. And therefore, for any element in G, we will have Gn G inverse is in G. Therefore, for all G belongs to G, n belongs to n, we have Gn G inverse belongs to n. That is the definition for normal subgroup. Now we shall consider an element in H. Now we have to show this is normal in H. So this is normal, n is normal in G. And now H intersection n is normal subgroup of H we have to consider. So consider an element in H. Suppose that H, to show, or yes, to prove H intersection n is normal subgroup of H, we shall show that for all H belongs to H, A belongs to H intersection n, H inverse belongs to H intersection n. So this we shall show. Now consider A belongs to H intersection N. A belongs to H intersection N. What this implies? This will imply A belongs to H and A belongs to N. Now let H belongs to H. And we have now H belongs to H and A belongs to H. Next, A belongs to H, or first we shall consider H belongs to H. Now H belongs to H, A belongs to H. So this implies H, A, H inverse belongs to H. You see this. H is in H, A is in H. What about H inverse? H inverse is also in H because H is subgroup. It contains inverse. And therefore all are in H. H is in H, A is in H, its inverse is also in H. And therefore H, A, H inverse is in H. Further, see, H belongs to H. And what we have? A belongs to M. H belongs to H means H is subset of G. H belongs to G. A belongs to M. Implies this H, A, H inverse. This belongs to N. Why so? Because N is normal. Since N is normal in G. So because N is normal in G, we have for every element G belongs to G, N belongs to N. This result G N G inverse belongs to N. Instead of G, here we are considering H. H belongs to G. Instead of N, we are considering A belongs to N, and that implies H A H inverse. So these are replaced. G is replaced by H, N is replaced by A, and H A H inverse belongs to N. And now you see this element H A H inverse is in H and H A H inverse is in N, and therefore H A H inverse is in H intersection N, and thus H A H inverse belongs to H intersection N, and this happens for all H belongs to H, A belongs to H intersection N. And thus this shows that H intersection N is normal in H. Normal in H. We are considering H in H, not in G. So hence H intersection N is normal. Normal subgroup of H. And this completes the solution for fourth. Assuming H is subgroup of G, N is normal subgroup of G. H is subgroup is used here since H is subgroup. Therefore, it contains inverse and A is in H. Therefore, we have it is in H, also is the same element is or product is in N, and therefore this product is H intersection N for every H in H and A in H intersection N, and that is the definition for normal subgroup. It satisfies and it completes the solution for fourth problem. Now we shall consider fifth one. Solution for fifth. Now what is the fifth problem? Suppose H is the only subgroup of order H in finite group G. Then prove that H is normal. H is normal subgroup of G. Now we shall suppose order of H is equal to say M. Let that is a solution for 5. Let H be a finite subgroup of order H, and we shall suppose it is equal to M. Finite subgroup of G, and order of H is equal to M, finite. So, and that number we have assumed as H. Order of H means number of distinct elements in H, that is given as M, and it is the only subgroup of G. G don't have any other subgroup. Then what we have to prove is H is normal subgroup of G. Now, because we have to prove that H is normal in G, that means it satisfies the condition, one of the condition for normal subgroups. Now, here what we shall consider is an element which is we will have GH G inverse. Now, for that purpose, let G belongs to G. Then, since H is a subgroup of G, we will have the element we shall consider a GH G inverse. Then GH G inverse. Actually, this is the set, and this is the set defined by GH G inverse, where H belongs to H, and this is a subgroup, and GH G inverse is a subgroup of G. See, this is a problem we have solved earlier. It satisfies the condition of subgroup GH G inverse. This set satisfies the condition that closure property, and it satisfies inverse property. You refer that problem we have solved in earlier problem sets. So this is a subgroup of G. Now what we shall prove that order of this subgroup is same as order of H. So we shall prove order of H is equal to M, and that is also equal to order of GH G inverse. Order of GH G inverse. This we shall prove. Let H has order M, means H contains M number of elements, and suppose the elements of H we shall denote by H1, H2, and so on up to Hm. These are the number of elements in H. And what will be the elements in GH G inverse? Therefore, GH G inverse, capital H, this will be, by definition, you see, every element of H is pre-multiplied by G and post-multiplied by G inverse. And therefore, from this definition, we can write GH G inverse with this H. And thus, first element will be GH1 G inverse. Second will be GH2 G inverse. And so on. The last one will be GHM G inverse. So these are the elements in GH G inverse. Now, the order, when the order of these two will be same, here, if these elements of GH G inverse are all distinct, we have considered the elements of H are all distinct. And similarly, if the elements of GH G inverse are all distinct, then the order will be the same, because the number of elements are the same, M here and here also M. Only the repetition should not be there. So GH G inverse, the elements, of GH G inverse are all distinct, since if they are not distinct, you see, suppose GHI G inverse is equal to GHJ G inverse, then this, what this will imply is HI is equal to HJ. Pre-multiplied by G inverse, this G cancels. Post multiplied by G, this G inverse cancels, and HI is equal to H, or cancellation law holds. HI is equal to HJ, means the elements are either equal or they are distinct. So that means the elements, all the elements, h1 is not equal to h2 here, because these are the distinct elements of h, and therefore the elements of this g, h, g inverse are also distinct, and this shows that number of elements in both the sets are the same, and therefore order of h is equal to order of g, h, g inverse. And we are, I shall write here, therefore order of h is equal to order of g, h, g inverse is equal to m. But what is given? It is given that h is the only subgroup of g, finite group g. So that is given, but given that h is the only subgroup, that means g don't have other subgroup. H is the only subgroup of G, and therefore we must have, see, this is also a subgroup we have written. G, H, G inverse is a subgroup of G. H is a subgroup of G, but G has only one subgroup, and that means these two must be equal. Therefore, we must have G, H, G inverse is equal to H. G belongs to G, and this is the condition for normal subgroup. This proves H is normal in G. We have the lemma for this. So this proves H is normal subgroup of G. And this completes the solution of fifth problem. So thus we have solved these few problems on normal subgroups. And next time we shall discuss the concept which is also important of homomorphism in group. Thank you.